And we are back, and so let's go ahead and think about how do we want to start to make measurements in Mathematica. Or make measurements in images and make measurements in Mathematica, or make measurements on images. Either way. So let's look at some example images. So sickle cell images, so cells affected with sickle cell anemia, and no sickle cell, so healthy red blood cells. So again, we can binarize images as we've seen previously. Works out pretty well for many images. We color negate as well. So I want to binarize my no sick images, and I'm going to color negate. And I'm going to do the same exact thing. I'm going to binarize those sickle cell images and get these values as such. So once I have these images in the color negate form, I can go ahead and start to make measurements on these images. So for example, for the white components in my sickle cell image, sickle, I could look at or measure the elongation of some of the white components. So like such. I could do the same thing for the not sick. I could also look at, for example, the elongation and what is the centroid. So for here. So what I can do is I can start to basically look at and grab some of those values. So for example, let's look at this. So I can go ahead and grab all two. So for example, or one of the things that we can do, actually we can start doing lots of cool things with this. So here it's telling me on sickle, let's go ahead and blow it up here. So I can go ahead and I could get coordinates. So for example, this is probably the centroid here, pretty close. So 59, 80, so let's see some values here. So it's probably, I would guess, the one with the largest elongation. It's probably 50, is it 55, 84? 55, 84. So it's probably right here. Anyways, we can clearly see the elongation of kind of those cells. And you can find the centroid too. You could also figure out what is the area. You could look at, also you could look at equivalent disk radius. So you could start to grab lots and lots and lots of parameters on each of those components. You could do, filled. Oops. Let's get out of here. We can do filled circularity. You could, again, you could kind of go ahead and look at that hollow one we were talking about. We could go ahead and look at all of these types of values. So, and we could compare that elongation to the non-sick. So for example, we can see some significant values, 0.74. So you could use this as a metric effectively to look at which of those cells are elongated versus not. Again, it's a little bit difficult to kind of, because the pixel sizes aren't the same, but you could do what are the filled counts of the images. We could look at the areas that are greater than 1,000. We could do for the same thing here. We could look at those areas, basically, we have to make sure that they're greater than 1,000. So I could look at some of these components here, and you can see here it's only giving me certain 11, the 11 component here. So it will keep and basically calculate kind of some of those values as well. So you see 11, 12 there. So it's a nice kind of feature to have. So I can look at area and adjacent border count. So give me the areas, the first number here, areas that are greater than 1,000, but my number adjacent border count is 0. So all the areas, only components that have no adjacent border features. So you can look at those values for sick and non-sick. I can count the perimeters. Again, there's lots and lots of different features here that you can kind of look at. And I could say, this could be my metric, right? Sickle greater than here. I could do the same thing for not sick. And you can see I have some of those values, but again, they're not kind of normalized by the feature. So if you choose, for example, 0.7, you might have some of those different values. But anyways, and I could actually pull out exactly the mass component that I want. So I could pull out that elongation that's greater than here. And we could do the same thing if I wanted to, for example, for, I could do sick, no sick, no sick. Let's do not sick, sick. Lipstick. So here you can see some of those components. And again, that's why you get the elongation here, because here we're touching. So again, when you get these values, you have to kind of see what is it actually referring to, right? So we can kind of look at those. We could also find, again, for the not sick, we could find the centers and then equivalent disk radius, and we could kind of plot our tracking. So this is pretty good, but we see we have some errors. So one of the things we can do is we can say, okay, give me all the values that aren't touching the border of my image. So if I do that, good, a little bit better. I still have these kind of small ones that aren't cells, right? So I could change based on my area. I could fine tune it a little bit more. What about this doublet here? You know, again, actually this didn't really do too much here. So for example, find cells here. Once I do this, I get this area, and now this is much better. So I'm basically eliminating the small values, eliminating the gigantic ones, and now I'm starting to get my images. You may be able to kind of fine tune this. I wonder if we do 800, what will we get? Oops, maybe 900? Let's do, maybe I need to do this. Let's do, how about this? Yeah, so you see, you can fine tune this pretty well. So we're pretty close to getting those values here. We can also help our, again, when you're doing image analysis, you really have to kind of think about how can I first clean up the image to make it what I want to measure. So for example, with these images that have the holes in it, right? I could delete the small components in my system. So see, I still have some small components. I could delete, basically removes things of 1 pixel. I could do 50. I could do 500. You can start to delete. You can delete border components, so anything that's touching a border. I could try to fill, if I'm just looking for the center of each of these cells, I can start to fill, and then I could also, again, remove all the components that are touching. So just grab the cells, and grab them with 1 hole, right? I could grab cells with 2 holes. So again, that doesn't really make sense. With 0 holes, you can kind of see those values. Adjacent corner count here, adjacent border count 1 or 0. So you can start to play around those values. So I can do the same thing with my images as well. I could find the centroid. So with that, and now I could plot it. So I find the centroid, I could grab all the components, I could plot these. How about just do medium? So you can see these on top. So now I can see the red dots, they're locating all those white points. Next time, we will get into how you can look at displacements in a series of images. So thanks, and I'll see you all next time. Bye.